here at ITI, and welcome to the Showcase webinar series. Today's webinar is titled Load Distribution, Trolley Beams, and 2 Crane Picks. This webinar is going to be great. We have 3 workshops that, and I know I didn't say this at the beginning, but they're going to make you think a little bit, so I hope everybody's okay with that. You should have received an email from me a little bit earlier today with a workbook that'll help you follow along and kind of maximize your learning in this period. If you didn't get the email, that's okay. There's still time. You can go to iti.com/showcase-webinar-materials, and the URL is on the screen there. And all you have to do is go to this site, click that link, and you'll have the PDF to help you follow along. So just before we get started, I only have a couple items I want to touch on, so let's get to it. So at ITI, it's our mission to be regarded as the world's foremost provider of educational and technical services for those who use cranes, rigging, and load handling equipment. We try our best to accomplish this on a daily basis through training courses at both client locations and our 3 North American training centers. One of our core values here is innovation, and we take great pride in finding solutions to all of the challenges brought to us by every single client. So that's something we do through our training centers, our courses, consulting. It's something that's a part of our day-to-day activities. So another way we try to fulfill our mission is by providing a number of crane and rigging resources to all who are in need. When you have some time, and I have to emphasize that because you can spend hours in here, please visit the URL on the screen there, iti.com/crane-rigging-resources. Here you can have access to things like ASME interpretations. There's 3 different blogs, info kits, white papers, ebooks, a pretty cool collection of crane and rigging videos, and so much more. Like I said, you can get lost in there for hours. So one other thing, if you guys think of something that you could be useful to you or that's valuable and it's not on our resources page, please let me directly know, and as I mentioned earlier, we can get a solution for you. I just want to mention 2 really exciting newish developments at ITI before I turn things over to Mike. So in January of 2015, a brand new program, Fundamentals of Rigging Engineering, is set to launch, and we really do have a dream team. I know that's kind of overused term, but it's true in this case. A dream team of developers and instructors who are putting the finishing touches on this program as we speak. What's different and really innovative about this is, and really it's one of the biggest benefits about the program, is the unique format. So most prospective students are going to be working full-time, and it's possible to complete this program entirely in an online on-demand format. There are hands-on options available as well for those who would rather go that route, but it's really just a great program. As you can see on the screen there, we have a few examples of screenshots of what the program participant might see. So there's going to be lecture recordings from those 14 Dream Team industry experts. And then what's unique about this is you'll see a stream of the lecturer as they're speaking, as well as notations that they make on their screen. So it's a pretty different learning format. It's not just a PowerPoint where somebody's talking and you're not interacting with them. It's great. And then in addition to the lecture recording, students are going to participate in discussions. There'll be assignments related to each module. Participants will be able to work in specific workshops for every learning objective, and then finally take some exams. So for more information on the course, and you can download the ebook that dials down a little bit more in depth on each specific module, just visit riggingengineering.com. And one more thing, I apologize, this probably won't apply to everyone on the line, but coming up in less than 2 months is the Advanced Rigging and Lifting Workshop in Edmonton. So this is a 2.5-day open enrollment event that is going to feature actually 4 of the developers of Fundamentals of Rigging Engineering as instructors. So, I mean, besides the obvious of being a great source of crane rigging and heavy transport information, Attending the workshop is a great way to discover potential gaps in your organization's current lifting and hoisting operations. You can get more information on the workshop at iti.com/Edmonton. So our host today is Mike Parnell, as most of you know, and I'm sure most of you on the line are at least somewhat familiar with Mike's work within the crane and rigging industry. I do want to point out that Mike volunteers his time to better the industry by serving as the vice chair on the ASME B30 committee and as the chair of the ASME P30 main committee. And on that note, I do want to mention Mike will be taking part in a live workshop on the recently released P30.1 standard, and that is taking place in less than a month here on May 22nd in Baltimore, Maryland. So if you'd like more information on that, again, you can email me directly at Jonah, J-O-N-A-H, @iti.com, or you can visit asme.org for more information. Whew. Okay, sorry for the overload of info there. But it's time for the main course today. I'm going to pass control of the screen over to Mike and let him take it away. One final note, if you guys have questions at any point today, please enter them into the question pane. I'll be collecting those as they come in, and I'll try to get as many as I can to Mike at the end of the presentation. So let me get the screen over to Mike. And whenever you're ready, Mike.
Okay, Jonah, do I have a good screen up? Let's ask that.
Yes, sir. You got the title screen there. Yep.
Okay, fantastic. Thanks, Jonah, very much, man. I really appreciate everybody joining me. We really, it's kind of a crazy week. Our prayers and thoughts are to those folks down in the Tornado Alley. I used to live there and still visit there on a regular basis, and hope the storms get dissipated and go away, and we're just hoping that folks and families are recollecting, and anything. A lot of volunteers are helping out getting everybody back on their feet. So we'd like to welcome everybody here. We have, as a general rule, we have in the neighborhood even today. Somewhere along 15 different countries that are participating. I see African metals or minerals is here, the Central Oceans, BP Alaska, and we have a number of folks around North America, and probably 25 to 30 states represented in their visitors group today. CB&I and Lane Construction and Maxim, we sure appreciate everybody participating, JV Driver, and Ness Crane, Ness and Campbell, and they have Navy Crane Center, Army Corps of Engineers. We have a lot of folks sitting with us today and getting ready to go forward with this. This particular workshop, if you don't have a calculator with you, you might want to pull out a smartphone or something with a calculator on it. People kid me, I kind of pull out an old abacus once in a while, but I've tried to upgrade myself a little bit. But this particular workshop is, it involves a little math, and we'll chunk through it, but we've really got some helpful formulas to get us through that. On the screen I've put up panel 2 from our Journeyman Rigging card, and this panel we're going to be particularly focused on this second and the third formula series here to help us figure out. The second one is, if you'll notice, let me just draw a line across here. The second one really is about knowing where the center of gravity is, but what we don't know is how much load is that going to put to our cranes or hoists or lifting system. So at the top of each of that inner placed boxes there inside the formula, we're going to look at share of load at A and share of load at B, and that's going to help us understand what we can anticipate for loading to those cranes or those systems. The last one right below it is when we maybe use an LMI or crane scale or dynamometer, and we maybe do a test pick at one end, test pick at the other end, and what that's going to help resolve for us is understanding the approximate center of gravity from A or from B. So this particular panel in your in the link PDF that Jonah made available to everybody, this is going to be very important to have in front of us, and these formulas that we have and they're boiled down to really non-engineers, status. It is the engineers will attack a problem like this with a sum of moments type formula approach, and we've broke that down to something where all of us can wrap our arms around and get to the same end goal and same destination, but a little simpler format for how we might want to approach our work. So let's use this formula series, and then let's tackle our first assignment here. This I'll put this got this up on the screen, and what I want you to take a look at, if you would, I'm going to kind of white this out for just a second. This right-hand image is the load that's been trolleyed from left to right. So our actual position 1 is on the left, and that's the initial liftoff. We have an overhead trolley beam that's supported by a building structure that's been permitted by the in-house engineer. So it has a total span there of, just for reference information, it's got a total span of 15 feet. And we're going to hoist this up, trolley over, and set the load down onto a rolling cart. And the rolling cart there's something of an obstruction here. We've got to pick it up, hoist, trolley, and set down. So that's our assignment. But what we'd like to know is, what's the resulting load on those two overhead supports, the west support beam and the east support beam? So right off the get-go, if we refer back to our formula, let's mark what we do know about this in the initial elements. I'm going to bounce this screen out just a little bit and bring this into view. I'm going to get rid of some of these notations here quickly so we can kind of get a clear picture. So what I'd like to do is ask you to, let's write in some information that we do know right now. We're looking for the share of load at A. We're going to call the west side A and the right side there east support B. So let's note that A is on the left, B is on the right. And on the initial lift of the 4,200 pounds, which includes, the 4,200 is the weight of the load, the rigging, and the chain hoist and trolley. That's in the information block in the upper right. So that's all suspended weight. So we're going to list R1. Run 1 is our 2-foot mark. And from there, we're going to figure out, well, how far is it over to our east support beam? And in this case, that's going to be 13 feet total. 8 and 5 make 13, and that's going to be run 2. So let's mark A is on the left, run 1 is with that at 2 feet, B is on the right, and that run 2, is 13 feet. And let's use our formula and insert the information that we have here. And on the formula that we're using is right there on panel 2. And note, what we'll do is, I'm going to ask you to do the same thing. Let's record that formula over to a spare sheet of paper or in the fill in the blank area here. We'd like to know share of load. We're going to use this first set of information blocks here. And there's a legend out to the right that shows what those items, what those variables represent. So let me pop a little sheet up on the screen here. And what I like to do is help highlight first, and I'm going to ask you to do the same thing with me. Share of load at A, kind of draw a line down there. Share of load at B, and we're going to write down our formulas here. And it says, and I'm going to leave space in between, I'm going to ask you to do the same thing. R1 and R2 equals total span. Drop down, leave some space. R2 run 2 divided by total span equals a percentage. And then we'll apply that percentage times the total weight equals share of load at A. All right? And then let's also write our formula in on the right side with share of load at B. And so the first line is the same. R1 plus R2 equals total span. In this case, we're going to use R1 divided by total span equals a percentage, and then percentage times weight equals share of load at B. All right, so excellent. So let's go ahead and fill in our information that we do know. Remember back on our drawing that we have R1 is 2 feet, R2 is 13 feet, and our W, we just haven't listed W yet. There's, excuse me, that's a magic marker there. So let's take W is 4,200 pounds. So let's put that into our formula set. So let's write that in. R1 is 2 feet plus 13 feet equals a span of 15 feet. We're going to use that R2, which is 13, divided by 15 equals a percentage. Let's punch that up and see what we get. And if we just kind of keep rounding generally to 2 decimal places, that's great. And if we get something that ends in 5, and then 0, then we'll probably use 3. But let's just stick with 2 right now. And I get 87% right there, 13 divided by 15. So we're going to take the 87% down on the next line times the total weight of 4,200 pounds. And that's going to get share of load at A is 3,654. Okay? And that's pounds. So I'm going to convert that. I'm going to write that over in just a minute to our answer page. Well, let's work our right side formula next. And please work your page as we're going through. We've given you all the documents. I want you to, this is full interaction here. So 2 and 13 equals 15 again. At this time, on the east side, which is a long ways away from the load, it's going to be a smaller value, smaller payload weight against that east support beam. And that is why we've got 2 feet divided by 15 feet. And that's going to give us a percentage, 13%. 13% of that total load weight of 4,200, and this is going to become an easy habit for us to get into. We'll just, our value there is 5. I got 546 pounds. So let's take those over to our page there real quick, and let's put those up on the screen as we need there. We've got to fill in the blank section right there. So I've got portion of load on the west beam, which is A, load of position 1, and I've got 3, 6, 5, 4. And the next one down, I've got load at east beam for position 1 is 5, 4, 6. Something I want to do really quick is make sure that 3654 plus 546, just as a double check, that's 0, that's 9, that's plus 1, 0, plus 1's 2, and that 1 is 4. So we did get back to our 4,200 pounds. That's a good double check. And one other thing you always want to do, because it's easy to get what we call the inverses that we're working with R1 and R2 in those positions. This is something we teach a lot is the load is the short distance. Just to double check, that short distance of these two is the 2 foot versus the 13, and that would result in the stout weight. And the long distance should result in the lightweight if we've got our numbers in the right place. And so the acronym, so if we say short stout, long light, did I get my numbers in the right place? That's kind of the question. You think about the pick point. Here's one other idea. The pick point closest to the CG should be carrying more weight. And that's the idea. This pick point is very close to this west side, and it's definitely should be the lion's share of the load there. In this case, it's 3,600 pounds plus 3,654. So we are, and 546 on the other side. So we do have our numbers. We think we got them in the right place. Okay, excellent. What we want to do then, let me get rid of these values here, these variables, and let's get a little bit of a clean slate. And what we're going to do right now, I'm just going to cover this guy up for a minute because we've already hoisted the load and we already understand what those values are. And now we're trolleying over to the laydown cart, to the load cart that we've got. And so our total, what we want to do now is identify, well, what is our total run 1 and run 2. And on our page, we've got, that's the initial 2 plus 8. So this is going to be 10 feet, and our balance to the east support is 5 feet. So right off the bat, some things naturally should be starting to come up to us. If you just take a look at 10 plus 5 equals 15, our distance actually hasn't changed. We're going to go do our formula here just a second. But, if you just put that 15 under each one of those distances, we have sort of 2/3 plus 1/3 equals 3/3, or the total distance. And so really our distribution of weight should be a 1/3, 2/3 split. We should really have, remember the center of gravity, the pick point closest to the CG carries more load. So really at the end of the day, we should be anticipating 2/3 of that weight's going to be on that east side, and 1/3 of that weight's going to be on the west side. So we want to start building a pattern in our minds. How are we getting these numbers, and how is this all coming together? So let's go back to our little formula, and let's fill in the values and information that we have. I'm going to leave this primary formula up on the screen, and we're going to just sort of fill in the new values that we have based on the new setting for the trolley system. All right, so on this one, run 1 we identified as 10 feet, and run 2 is 5 feet. And so what's our value? Then our total span is still 15. This time we're going to take run 2, which is 5, divided by total span of 15. And that's going to get us that percentage that we were talking about a minute ago of 0.33. We'll apply that percentage down times the 4,200. Give you a second here, see what we get for what's 33%. 0.33 times 4,200. And I hope we all get to the same place here. I got 1,386 pounds. All right. Let's fill in the information to the right, to the share of load at B on the east side. And we're going to start out with our initial information first there. 10 and 5 is 15 feet. Now we're going to use this R1, so that's going to be 10 foot divided by the 15 foot. That's going to get us to 67%. 10 divided by 15 is 67%. Let's apply that to the last line, 0.67 times a weight of 4,200. Let's punch that in our calculators. 67% of 4,200, and I hope we get down to 2814. Okay, so we're going to take those values, go over to our main page there, and let's scroll up here just a bit. And we should be able to roll in those values into position west beam loading on position 2. We should have 1,386, and then position on the east beam for position 2, we should have 2,814. And then here's another, remember the question we asked a minute ago. Let's add these two up and see if we get back up to 4,200. So I've got 6 and 4 is 0. Carry the 1, I got another 0. Carry the 1, I got 12. 2, carry the 1, I got 4. So we have 4,200 as our target point there, and that makes sense. And I think the question we want to continue to ask ourselves is that light weight, the 1,300, 1,386, does that make sense on this side, 1,386? And does the 2814 make sense over here for our end result? So 2,800 on the right side, 13 and change on the left side. And so our center of gravity is positioned closer to that east side on B, further away from the west side at A. And so we've got more load on B, less load on A, and that makes sense too. Short stout, long light. In this case, they've switched positions from the first example. Okay, so the idea there is to just kind of get our heads around what will transition, what will happen when we move loads across. You can actually, it's kind of weird, but we we suspend a trolley beam. We have a couple of hoists, and with a portable trolley beam that's got some stops on it, so the trolley can only go so far. And we'll actually roll out a load, and these trolleys are suspended by dynamometers up to a support system. So, and you can actually see the values change on the dynamometers as we move that load from left to right. And it might start out 1,000 pounds here, relatively speaking, and 0. And then as we trolley across, we might stop here and it might read 600 versus 400. And as we continue to trolley across, we might end up over here at 200 on the back side and 800 on the lead side. You can actually see the values change right up on the dynamometers as we make the transition. So it's a very good learning exercise. We use it all the time in our master rigger and our journeyman workshops for advanced learning, and it's just, you know, numbers tell the tale, and it always makes a lot more sense when you can see it a little more. It locks it in better for us, and so we get a better confidence when we're starting to run numbers and do some estimations without having any of the electronics or some of those scale or lifting devices. All right, excellent. Let's take a look at this next one. By the way, we will be, Jonah will be putting an answer key up on the available for everyone when we get all done here. And so if you don't pick up a number that we're using along, don't worry, we'll have an answer key for you with all this detailed out for you just as we move forward. So let's take a look. Here's the idea. On this next problem, we have two double hoist hook on the same bridge. It's on a bridge crane, and right up above there you can see we've got a 30-ton hook and we've got a 5-ton hook. So we got a big brother and a little brother on the same bridge. And the idea is we're picking up this large shaft with 2 gears on it, and we want to move it, transit it, and eventually we're going to have to land it. So, but before we get going, we want to make darn sure we have each hoist has the rated capacity necessary to make this load move. And since we've got two different hoist values, we want to make sure we're rigging them up to the correct end. Or would we need, for some reason, to, gee, we're going to overload this or that, we might have to actually, instead of rigging to that top gear, we might have to rig further out or further in based on the center of gravity. Or in this particular case, on the 5-ton, are we too close into the CG? Do we need to go out? What do we need to do to help make sure we stay within the rated capacity of those hoist systems? So knowing what we're picking up is really important, and that's first up. As you all know, we shouldn't be lifting anything or handling anything that we don't know the anticipated weight or tension that's going to be applied to that hoisting system or load handling equipment and the rigging to make sure that we're staying within its rated capacity. So let's do this. Let's take a look. Let's identify 3 significant pieces. We're going to challenge ourselves to tackle this in 2 steps or 2 stages. We're not going to eat the whole pie here at one time. So let's just deal with, and we're only 2 items at a time here. And notice off to the left there, we've got a shaft of 10,000 pounds, and that small gear or little gear is 5,000 pounds. So what we want to do is find the combined center of gravity for each one of those 2 pieces. And once we do that, then we'll come back and find the CG of those 2 combined with the big gear. So that big gear is our last step. We won't worry about it right now. We're just going to work on those 2 first components. So let's take a look at the shaft. It's uniform in its length. There is a hole in it. It's not completely solid. There's a hole there, but it's at 10,000 pounds, and the overall length of that shaft is 30 feet. And so at 15 foot, we're going to put a little mark, and this is certainly not to scale drawing, but we're going to put a little mark, you know, somewhere about where we think the center of gravity is for that shaft, about the mid-span at the 15-foot mark. And let me move that over just a little bit. And then we're going to put a CG or bullet mark where we think the center of gravity is for the shaft, or the little gear is, the small gear. So it's really between two known weights. We've got one's 10,000 and one is 5,000. Now, if it's, we're just going to mark on the page here for a second. If this is 15 feet from the end of the shaft to the approximate CG of that center portion, and it's another 15 feet. So we're 15 and 15. We're dead center of that shaft. And this guy is 4 feet from the end. Notice that little 4 down there. So we're 4 feet. So really kind of working from the right end to the middle. Now we want to know what this total span is. That's an important number to us. So really I could just take 15 minus 4, the right-hand side, 15-foot length, this 15-foot length, minus the 4 feet from the end of the shaft to the small gear, and I've got an 11-foot span there. And that's an important piece of information. So what we might do, let me clean this picture up just for a second. This stuff, get rid of this for a minute. So I've got if you kind of think about a big old ball and box right out here, I've got a weight that's, this shaft is 10,000, and I've got a small weight over here, and that little guy is 5,000. What I really want to know is then from those two, which is 11 feet, where is the combined center of gravity of those two pieces? That's the secret. That's the goal right now for what we're trying to arrive at. And if you remember from our last workshop, what do we already know? We're now, instead of runs or distances, we're going to tackle it in weight. And so we've got in effect, I've got a 10,000 pound weight and a 5,000 pound weight. And those two combined at the moment would equal 15,000 pounds. Do you remember from our last exercise, if we just take the total, all parts divided by the whole, what we just discovered was, well, we got a 2/3, 1/3 load split here. 2/3 of the weight's in one place and 1/3 of the weight's in another place, and we're just trying to figure out how do we apply that. And the short of it is we're just going to apply that to the 11 feet. I mean, somewhere along there is just a big barbell, and we'll put two big weights, one big weight at one end of the barbell and a small weight at the other end of the barbell, and where do we pick it up to balance it? Where is that perfect balance point about which the entire combined weight is centered or concentrated? So that's what we're going to do here. I'm going to pull up a new page, and if you would, let's see, let me get this going here. Let me pull this down out of the way for a minute. And if you'll notice with me on our, we'll go back to panel 7 right there, and we're going to pull up this other formula. And this is the one that I've got highlighted in green. It's known weights. I do know the weight on the left, do know the weight on the right. What I don't know is where's the center of gravity from A and where's the center of gravity from B. So we're working off this bottom formula set here. CG in feet from A, CG in feet from B, and then we've got some legend information. So let's keep that page out there in front of us. This is page 8 of our handout, and we want to keep that active because this is the formula that we'll be using for this next series right here. So let's take a look then, and we'll pull this up. Let me get back to our challenge page here, and kind of get that in front of us. I'll get rid of some of this information. It gets a little cumbersome sometimes, so get rid of that. And let's just put it right on the screen so we can kind of work through this fairly quickly. And the formula, what the formula says to do is to take, it says to take weight 1 plus weight 2 equals a total weight. I'm going to leave a space, and I'm going to ask you to do the same thing. Weight 2 divided by total weight equals a percentage, and then a percentage, that percentage times the span, which is 11 feet, is CG in feet from A. And we can just draw this line down here. We're going to do the same thing on the other side, because this is the A side and this is the B side. So weight 1 plus weight 2 equals a total weight. In this case, we're going to take weight 1 divided by total weight equals a percentage. And then percentage times that span again is CG in feet from B. All right, excellent. So let's fill in what we do know. We were just looking at that, so we know the weight 1 is that big is the shaft itself. And I'm just going to put 10K for 10,000 plus 5K for the small gear equals a total of 15,000. Excellent. So let's complete the next line. What is weight 2? Weight 2 is 5,000 divided by total span, or total weight of 15, and that's going to give us a percentage of 0.33, 33% of that 1/3 that we were talking about. In this case, we're going to apply the 0.33 times the span and find out how far away from that center shaft point is the approximate CG, and that span was 11 feet. And that's going to give me a value. Let's punch that at 0.33 times 11. And hopefully that's going to give us 3.63 feet from A. And we're going to put on here just a little bit of a hack mark. So I know that this is 15 feet already from the left to the center point. Now I'm going to go over another 3.63 feet. And this is my approximate CG for the two pieces. I'm going to double check that by working the right side of the formula, and I will always double check our work. So weight 1, 10,000, weight 2, 5,000, total 15,000. Weight 1 is 10 divided by total weight of 15 equals a percentage, in this case 67%. Excellent. Okay, we're going to apply that 67% times the span, so 0.67, let's punch that up. 0.67 times 11, and that should give us 7.37 feet. All right, one thing we want to do then at that point is double check. Well, let's see, does 7.37 and 3.63, does that equal back up to 11 feet? And it does. 3.63 plus 7.37 equals 11 feet. So we got our homework done there. Which end is the heavy end? The shaft is the heavy end, and the little gear is the light end. And so we're only going to be a little distance. So short stout, long light. So I've got short stout right there, long light on this side. So I am only 3.63 feet away from my original end. And there's my combined CG for the two pieces. So in thinking about that, I'm going to put a new value. What is 15 plus 3.63? Let's just kind of work from the west end for a second and get a common point in our heads here. So we should have a value of 18.63 feet from the west end, if that makes sense. Okay? So let me get rid of some of this information here. I'm going to come back, and I'm just going to use some of my same formula here in a minute. Get rid of this stuff. You've got more paper than I do, so go ahead and clear yourself some space. Let me get rid of this. So we've got 18.63 feet from that end to the approximate center of gravity of the two pieces. What we haven't dealt with yet is the big gear. Now the big gear, let's see, where is the big gear in the 18.63 feet? That big gear is right there at 6 foot at the center of that gear. So what we'll want to do then is I'm going to take the 18.63, subtract that 6 foot from the west end, and I'm going to get 12.63 is the span. That's my new span, and that's what I want to record. That's the distance. I'm going to put this in red. That's the distance from this big gear to the shaft small gear combined CG. 12.63 is that. All right, 12.63. That span, that's a very important piece of information that we need right there. So what do we know about the weight of the big gear? Everybody see that? It looks like the big gear right there is 15,000. And what do we know about the weight of the shaft and little gear? Shaft and little gear, if we add those two up, that's 15,000. Okay, so we got 15,000 pounds here. We got 15,000 pounds there, and we got a span of 12.63. So let's put that over in our formula set. We're using the formula off page 8. It's the weight 1, weight 2 type formula. Let's put in what we do know. Weight 1 is the big gear, so that's 15,000. Weight 2 is the shaft and small gear combined. That's 15,000. So now we're up to a total of 30,000 pounds, which is correct. That's all parts combined. Well, this should be easy for us, piece of cake, so we'll take 15,000 divided by 30 should give us 50% of the load. And 50%, let me get rid of this bottom part down here for a second, get this out of our way. And we've got 50% for the percentage. The span is 12.63 equals, and that distance, I've got written down here 6.315, and reason I've written that down, it ends in 5 and then 0, and we want to just go ahead and use that value for just a minute. Let's go ahead and complete the other side, which should be identical, 50,000 plus 15 equals 30. It's a 50-50 load split, so W1's 15 divided by 30 equals 0.50. 50% of the same span, 12.63, should get us to 6.315 feet. Okay. Question is, did those two values add back up to 12.63? Yes, they do. And what we'll do then is we're gonna put a hack mark right in between those two that run their distance there, and I got 6.315 on each side of that. And I'm just going to draw that center of gravity bullet right there for just a minute. So the total combined center of gravity for all three pieces, now we'll kind of get rid of some of this other stuff here. Total combined CG for all these other pieces, for all three pieces together, is at that point. Now let's kind of make a mark here, make a note on our drawing. Well, gee, if this is 6 feet from the end to the center of that shaft, and that's another 6.315, so we add those two together, we get a total distance of 12, and we'll round this, 12.32 feet. 12.32 from the end of the west end to the CG. That's a real hard number. We need to keep that number in our heads here. 12.32 feet from the west end to the CG. That's our bullet point. Okay. All right, excellent. So that's important for us to know, because we've got to figure out how much load we're putting on each crane. So now we know that we are then, in this case, so let me answer the question down below here. We know that that little guy is, the center of gravity is 12.32 feet from the west end. I've just answered my first question. The next questions are, how much load is on the 30-ton hook? How much load is on the 5-ton hook? That's really that's the whole point, of reason why we're having to kind of monkey through this. I know it takes a lot of time, but just think about this. We don't want to overload that 5-ton hook and pull the whole thing down. So we want to make sure we can lift it and in our anticipated method, and we can handle it. So here's the idea. take a look at what do we know right now. We know the capacity of the cranes, that's a given. And what we do know is the distances from the pick point, which is the center of the big gear. That's a pick point right there. It straddles the middle of that gear. And we know that we're going to be picking from the center of that small gear right there. Well, this distance we do know is 6.32 feet from there to there. So we do know that value. What we don't know is, well, gee, what's the distance right here from the CG to that small gear, which is where the 5-ton hook is picking? Well, what we have also available to us is that value down there below. That's a 20-foot span hook to hook. So let's do this. Let's take 20-foot span minus our known 6.32, and the balance there, that balance distance, is 13.68 feet. All right, excellent. We just discovered our distances. Now, just for grins, which one do we think is going to carry more load, the 30-ton or the 5-ton? Oh, excellent. Getting a little feedback here from a few. 30-ton is going to carry more load. The center of gravity is closer to that 30-ton hook and further away from the 5-ton hook. And we're going to find out very quickly what those what the actual payload is of the 30,000 pounds against those two hoists. So let's take these two numbers that we know, 6.32, 13.68, and let's go over to our run 1 and run 2. If you remember we just used this initially. So we're going to use the run 1, run 2, this share of load at A and share of load at B. A whole lot of rigging decisions actually come right from these two formulas in our card, and we're going to focus on discovering what those values, those loads are to those two hoists or cranes. So it's the center formula we're using, and we'll put this up on the screen here. Let me go back to this little formula I've got preset here for us. So we're going to use share of load at, what's the share of load at A, which is the crane 30-ton? What's the share of load at B, which is the 5-ton? And I'll make a note up there that which ones we're talking about here. So share of load at A, which is the 30-ton, and share of load at B, which is the 5-ton. Let's put in what we do know. And I'm carrying information over from the drawing. 6.32 is run 1, and 13.68 is run 2, and those two add up to be 20 feet. Excellent. All right, what we do know, we've just done it just a few minutes ago. We'll take that 13.68 divided by our total span of 20 feet, and that's going to give us a percentage of about 68%. Now what do we do? Let's take that 68%, let's keep going down our formula there, times total weight of 30,000 pounds equals a resulting load to the 30-ton crane of 20,400 pounds. Excellent. Perfect. Okay, give you a few minutes, then take a look. Let's get the weight on the 5-ton crane. And I'll slowly start putting this up, and let's go ahead and put our data in there that we know, 6.32 for that run 1 and 13.68 for run 2. We do know that equals 20 feet. Carry the formula down, we'll take a look at 13.68 divided by 20-foot span, and that's going to give us a percentage of 0.32. We're going to carry that down one more step. What is 32% of 30,000? So 0.32 times 30,000 equals, and we got a value there of 9,600 pounds. Excellent. All right, good thing for us, because guess what? Well, on the 30-ton crane, we got 20,400. 30 tons is 60,000, so we're in great shape there. We got 20,000 pounds of load and change on a 60,000 pound crane hook. On the other side, I got a 5-ton hook, which is 10,000 pounds, and I'm only imposing 9,600 pounds. That's a 96%. That's a pretty high lift, isn't it? But it's still within the capacity of the crane, which should be okay. Should be in good shape. Crane's inspected, and it's all healthy, and everything's good with it. So let's take a look here. So then we're going to transfer our information over. Let me pull this up to the top so we can see this. So I've just discovered we're going to be able to put 20,400 on the 30-ton hook, and we're going to put 9,600 on the 5-ton hook. Excellent. So we are within the rated capacity. Okay, super. All right, the next item. Whew, that's a lot of work. You guys are doing great here. The next question is, here's the process and procedure, and this is kind of where we get into a bit of a bite sometimes, that, well, what's the job? Now that we know, let's just say that I'm going to put that CG. This is not perfectly to scale, but gives us the idea. And I'm going to put that center of gravity, let's just put it right in here somewhere. And it's, so we know we're about 6 1/3 feet from the 30-ton hook and over 13.5 feet from the 5-ton hook. We know where we're at. But what we got to do is put this shaft and double gear set onto some stands so we can do some repair work on the gears. And these two stands, we've got a little picture and illustration that's been provided for us up there in the upper left. And this gear, the stand looks like this, sort of a big old sawhorse that's been custom built to accept the shaft at both ends. And we're just about ready to lower the shaft and double gear set onto those two stands. Now, I want you to take a second and think about this. We're about to lower this down, and this shaft is going to come down into that saddle on the west side and into this saddle on the east side. And it's going to cradle in those saddles. Now, the question is, which end do we lower first? You know, we've got two separate hoists. They run at different speeds or different parts of the line, different capacity, different drum sizes. Everything runs different. So which end should land first? That's sort of the question. Which end should land first? Should we land the west end first, or should we land the east end first? Take a look at it, and it can cost us big time if we don't get our procedure down right. And that's really the bigger part of why we're doing this workshop. So I want you to take a look at it just for a second and see what your thoughts are for the left side and the right side. While we're doing that, let me turn page here and get some numbers up. Okay. So that's our effort here. So the question is, and now I want you to think about this, that we can have in some combination, and I'll put these in two different colors. One, we can have the 30-ton crane and that far east stand supporting the shaft if we lower the right end or the east end first. The other decision can be, and I'll get rid of this little guy up here. The other process is, well, we could decide, let's have the 5-ton crane hold up, and we're going to lower the 30-ton, and we're going to let that end sit on the shaft. That's the whole idea. And something should jump out at us as becoming very, very quickly apparent. Take a look. And in the first case, I'm going to put a thin line right down here. If we land the east end first. Look how close the 30-ton is and how far that east end saddle is. And that's a nice proportion, because what we're doing is we're resting that further away. Our pick point basically changes from this line to this line. And it's going to add a little weight to the 30-ton crane, but we probably can survive it since we got 60,000 pounds of capacity. To do it otherwise, let me back these out for a second. And let's do this. Use the yellow here. Look how close we are with that 5-ton hoist to the CG, and how far we are with that west end saddle, that west end shaft stand. And in this case, not to be, we're not perfectly 50-50, but it's pretty darn close. And if we remember something, that the total is about 30,000 pounds, we're almost 50-50, where we're going to see somewhere well above 10,000 pounds on that 5-ton hoist if we decide to lower the west end first. That's the whole deal. We have a great opportunity here to overload the 5-ton hook, for sure. That's the main element I want us to walk away with today. When we're picking in two places, here's the deal. If we're picking in two places, we're going to pick here and pick here, but we're going to land in two other places, out there and out here. Be really careful. Even a mobile crane or overhead crane or tower crane and something else, or I mean, I tell you what, you can get in a big bind in a hurry by picking at 2 points and landing in two other points based on what the integrity and capacity of those two hoisting systems are. So it's a real procedural decision, and we really got to hammer that down. I'm going to expedite this for us just a little bit. Excuse me for that. I'm going to, let's take this on the next page in our PowerPoint that you have there. You got a whole gob of numbers. And I don't want to burn up a lot of time right now, but I know that you can get to these values. And I'm going to run this down for us real quick so that we can kind of get our, just put a CG bullet in here. And so if we contact the, here's the idea. If we contact the east saddle, let's see, east saddle, we're gonna do this first. Let's do the 30-ton hook and the east saddle as that combination. And I'm going to put the values up there. I know you can add up all those numbers and do exactly the same formula that I've just done. But if we do this first, what we started at was our initial numbers were on that east hook. We were at 20,400. Based on now the new distance out from that 5-ton hook to the east saddle, that's going to go up to 21,900. And what will happen at the east saddle is going to be 8,100. So the east saddle, when we land it, when this comes down and lands there, the 5-ton hook lowers, we land it in the saddle, the bearing weight is 8,100. And there is some argument, and what we did was we went to the outside of that saddle edge to get kind of the worst case. And just so you notice, it would hit the outside edge first, and once it settles down flat, it'll be in the center, more or less in the center of that saddle width. So we're just kind of taking a worst case. So we got 21,009 and 8,100, and those add back up to 30,000 pounds. So this first is 5-ton hook lowers, puts it into the saddle. Second step is to put the 30-ton hook, lower it down, and put that into the west saddle. So those two values result in 21.9 and 8,100 on the east end set down, and eventually we'll pay off the load to the 30-ton hook, and it'll set down into that west saddle. Now let's consider the alternative, and let's consider bringing this west end down first. Let's see what happens there. Initially, we had what was it, 20,400 and 9,600 for suspended weight, and in this case, this load out here to this saddle will be 16,500. Because you guys can do the run 1, run 2. You can all come up with this information since we've already been through those formulas. We know what those runs are. You can assign, this might be A and B, and this is going to be run 1, and run 2 will be those spans or distances to the center of gravity and so on. So we already know all that stuff. We've already done it, and now we're going to discover that the 9,600, which is the kicker, 16.5 on one end, and what's going to happen is it's going to grow to 13,500 pounds. And we are in an absolute big honkin' overload. And we got to be really careful. We are now at, we're at 35% past the 5-ton hook capacity by lowering the west side first and then eventually lowering the east side. The one that's, we always want to make sure that we're double checking our values. Let me go ahead and put these numbers on the next page. So let's record these. And these are the values I've got. I know you guys can do the math, and gals can do this. So I'm going to put 21.9 and 8,100 for the first case. In the second case, we're going to put 16,500 and 13,500. Those both add up back up to 30,000. And this is an overload for the 5-ton crane, 5-ton hoist. So we want to be, we just discovered, hey, we can get the weight. Hey, we can get the center of gravity, no problem. We can make sure that we're within rated capacity. Now what we're about to do is set these down on supports. And oh my goodness, we're going to be overloading one crane if we don't do it in the right step-by-step procedure. That's the big takeaway here. Okay? All right, excellent. And there is an answer key, of course, for this, and that's available to you once we conclude the webinar. Just about finished. I wanted to throw something up to you. We have kind of a fun Mike's Rigging Mystery set that we've used over the years, and we created two brothers, Stinker and Tinker, and if you'll notice that this all kind of plays out into the real life world here. They've got deer meat sitting up on a 25-foot pole or 25-pound pole, kind of tied up at the center right there. And the real question is, when they started carrying all this, this is the same exact thing that we get into for rigging and load distribution in 2 cranes, but we got 2 people here. That the deer meat secured at the 25-pound pole at the center. They started carrying it, and they were both 3 feet from the securement point, and that resulted in 75 pounds apiece. 75 pounds there, 75 pounds there. But over time, Tinker gets tired and he starts to slide back along the pole. Now he's at 5-foot distance instead of the 3-foot distance. Does that change the weight to each brother? Absolutely. You can tell the direction they're heading. Tinker must be having a pretty good jolly laugh over this whole thing. So, you know, if we just think about and get back down to what's simple. Well, I'm at 3 feet, and I got 5 feet, and the total span is 8 feet. If I just divide all parts by the whole, 8, 8, and 8. So I've got what do we got? 32. We got 3/8 on one end and 5/8 on the other. And you remember that inverse, that transition there. So actually, we've got 5/8 of the load up here on Stinker and 3/8 of the load back here on Tinker. The further away he gets away from that meat, less weight he's carrying. Pick point closest to the CG carries more load. That means Stinker's carrying more load. And in pounds, That's going to result in about 94 pounds and 56 pounds. So we've got, those brothers are going to have a discussion and a tumble when they get all done, but Tinker's gaining weight all the time and Tinker's moving away from it. So it's just sort of a little bit of a fun deal. We've got 110 workshops in that Mike's Rigging Mysteries set, and it'd be great if you want to pick up some interactive workshops that are problem solving, and they've all got answer keys with them. The bookstore's got them, and we've used a lot of those also in our Master Rigger Advanced Rigging, but we got 10 little workshops that are rigging in the outdoors where these guys show up and present a couple of fun little, you might say, homegrown backyard rigging activities that kind of give us a pause for thought. So, okay, very good. Questions and answers. Jonah, do we have, don't know if I got all the answers. Are there any questions by anybody that have been coming in during the webinar, or are we in pretty good shape? What do we got?
We're pretty clear right now. Either we got some shy people out there, or they were following along and they're busy writing in their workbooks, but I don't have anything right now.
Okay.
If something does come up, please send me an email, and even though it's after this is gone, the recording will be posted in 24 hours, and I can relay any questions somebody might pick up at a later date.
All right, and I want to say thanks to everybody, but I want to really reinforce the idea. There's 3 axioms of rigging, and that's load weight, CG, and rigging method. And those are the 3 basic starters for anything that we want to do in rigging. What is the weight? We've got to do weight estimation using techniques, come up with the weight, and whether it's solid mass or combination of gears and motors and pumps and electric switch boxes, whatever the items are, what is the weight? You've got to get a total weight. And second, where's the center of gravity? Where's the approximate CG? Because always that center of gravity is going to dictate what my rigging tensions are. My rigging tensions are going to influence my rigging methods to some degree. Do I basket it? Do I choker hitch it? Do I direct connect it? How many cranes are going to be picking up? 1 crane. Well, all the rigging is going to come together, at some peak point, or will it be going straight up? And do I have some alternatives there for rigging methods? So, and because it all plays out. So, load weight and center of gravity will always drive us to picking a rigging method that'll get us good to the finish line, that will ensure that we have sufficient capacity and rating for all the rigging, slings, shackles, come-alongs, chain falls, all the things we're using. So those are the 3 things. And if you wanted to really start, if you got a rigging program, you need a rigging program, we always want to start to emphasize that with the new folks coming along. What's it weigh? Where's the center of gravity? And what is the rigging method we want to choose to provide stability and proper and correct rated capacity for the rigging included? So that concludes our day. I really appreciate everybody participating. We look forward to seeing you on the next webinar that we've got. We've got a number of activities coming up for the summer. Stay in touch, and we'll make sure you're informed about those programs as they come up. This is Mike Parnell signing off. Thanks so much, and hopefully we'll see anybody wants to come to the the critical lift planning for the P30, ASME P30.1 program in Baltimore. That's in Baltimore on May 22nd. And ASME.org has that on their website. You could also contact ITI.com, and we can get you the same information. So have a great week and weekend coming up, and we're looking forward to visiting with you in the future. And thank you for being such a good friend to ITI and participating with us along the way. Take care, and we hope everybody has a safe day.